Hello everyone, my name is Gonzalo Ferrada from the University of Iowa, and today I will talk about the improvements that have been made in recent years to better simulate biomass burning smoke plumes with a special focus on Africa. So why do we care about the smoke in the atmosphere? Well, globally fires are responsible for the release of around 2 petagrams of carbon emissions each year. In this figure, you can see the major regions that contribute the most to biomass burning emissions. Many of these fires are man-made burns that happen seasonally, but others are due to natural causes, such as lightning that can trigger very large wildfires. Among all the gases released, there are also several greenhouse gases such as CO, CO2, methane, water vapor, and others that contribute to global warming. Also, fires release several hydrocarbons and nitrous species that are ozone precursors. In addition, aerosol particles interact with solar radiation in a way that they can absorb it or scatter it. On top of this, some of these particles can serve as cloud condensation nuclei that alters the formation of clouds and precipitation processes. And of course, when urban areas are exposed to poor air quality episodes, you can create health emergencies and interference with human activities such as the economy. If you watch the news, you may remember around 2 years ago several stories about the bushfires in Australia. In this animation, you see a variable called AOD, which stands for Aerosol Optical Depth. This is a dimensionless value that gives an idea of the extinction of sunlight by atmospheric aerosols, which is proportional to the concentration of aerosols in the atmospheric column. A value of around 1, that is the blue to purple colors in the animation, indicate a dense layer of aerosols that we commonly associate to orange skies. Here you see the Australian fires since they started in early November 2019 and continued for the whole austral summer. These fires were so massive that the smoke traveled the southern hemisphere several times and it was clearly visible from space. Recent studies have shown that these fires release enough material that cooled down the atmosphere for months. In North America, we have had very active fire seasons during the last years. This is an example of the fires occurred during the summer of 2020 that left damages in the billions of dollars. Here, the smoke reached its peak in mid-September, when traveled and covered great part of North America. In this animation, similar to the previous one, you can see how the smoke crosses the Atlantic and affects Europe. Then it gets mixed with the smoke from the Siberian fires and eventually reaches the North Pole before it completely dissipates. Large fire events are capable of injecting smoke in the stratosphere when it gets trapped and the deposition rates are low. For example, this paper from Nature highlights the fires occurred in British Columbia in 2017. The smoke reached altitudes up to 20 kilometers and injected material comparable to a moderate volcanic eruption. The last example are the fires in tropical regions. Africa has the most intense fire activity of the world, accounting for more than a third of the global carbon emissions from biomass burning. In tropical regions, fires occur mostly during their respective dry seasons. For the case of Southern Africa, this is between July and October of each year, with a similar annual cycle observed over the Amazon and South American savannas. Given the importance of fires in Africa and the not so well understood interactions of smoke with the clouds, several field experiments have been carried out in this area in recent years. Now that you know all the impacts of fires and smoke in the air system, I will introduce you to atmospheric models by giving a brief history. Then I will talk about biomass burning emissions. How do we quantify the amount of aerosols and gases that fires emit? And at the end, I will discuss the physical and dynamical processes of smoke plumes. So let's begin with part 1, atmospheric models. Models use a grid where they calculate and apply all the equations that describe the atmosphere. This is momentum, energy, mass conservation, etc., and report the mean conditions in each grid box. Models can have many vertical layers depending on the purpose. The generic way that models work today is shown in the conceptual map in the bottom. We collect as much observational data as possible from weather stations, meteorological balloons, and satellites to create the initial conditions for the model. After this, we create what we call an analysis, where we fill all the data gaps. For example, the figure at the top shows the distribution of global meteorological stations. We have plenty of data in Europe and North America, but very few in the rest of the world. So the analysis is just a guess of the model to fill those gaps and give a realistic representation for the model to start the simulation. After this is done, the model can initialize and produce forecasts or other kind of analysis. Weather and climate modeling has been improved notoriously in the last decades, and is still something that is more limited by computational resources than what we know about the atmosphere. This graph shows a time series since 1981 to 2017 on how the weather forecast from the ECMWF has been improved progressively. Since mid-2000s, we have 3-day forecasts with more than 95% accuracy. But you can see that we still cannot have reliable 10-day forecasts because the atmosphere is too chaotic and we do not have enough observations to start the models as I showed before. The main things that can improve the forecast are better observations. That's why more satellites are set to be launched in the following years, and better constraint of the processes that are not solved explicitly by the models. These are the so-called parameterizations. Since the mid-1990s and early 2000s, we incorporated chemical species, chemical reactions, photoreactions, aerosols, aerosol hygroscopy, depositions, etc., and their interactions and feedbacks with the meteorology, such as clouds and impacts on shortwave and long-wave radiation. We are in a point where we have very sophisticated atmospheric models and several groups worldwide work together to improve them. The major limitation we face today is limited computational resources, especially when we incorporate chemistry and aerosols, because of the hundreds of reactions and interactions makes the simulations around 5 times more expensive than when using just meteorology. There is just no supercomputer that could handle the levels of memory required for such calculation at very fine scales. That's why we are forced to use approximation or these parameterizations that can introduce errors. Chemistry transport models use several sets of emission inventories to reproduce the atmospheric composition. For this, we have several categories. First is fire emissions that consider all open biomass burning emissions, and there are several datasets that provide this information based on satellite observations. We also have anthropogenic emissions that include industries and transportation, among other human activities. We also have biogenic emissions that include soil, fauna, and vegetation emissions. And finally, we also have other kinds of emissions like volcanic eruptions, airplanes, ships, and others. After this brief history of the models and description of how they work, I will go now to part 2 to discuss biomass burning emissions. As I mentioned before, there are many biomass burning emission inventories. Here you see 4 major ones. All of them use the MODIS active fire product to locate and estimate emissions. Some of them, such as GFED and FIN, use estimations of burned area to estimate emissions, while others like QFED and GFAS use the fire relative power. With the increase of computational power, models now consider hundreds of chemical and aerosol species and are capable of to solve it in very fine grids. These inventories are widely used, but they often offer a limited number of species. This can be a problem when running model simulations with complex chemistry, since the missing species begin as zeros, which can have an impact on the formation of secondary species, such as ozone. In addition, except for FIN, they offer emissions gridded at resolutions not higher than 10 kilometers. This can be a problem because fires in fine model grids can be misplaced, and then the smoke is subject to different meteorology and circulation patterns, which is particularly important in complex topography. For example, fires in the Rocky Mountains. Because of this, and aiming to solve these problems, we created a new open biomass burning emission inventory called Virus-Based Fire Emission Inventory, or simply VFE. Here we use the fire relative power from the VIRS sensor on board of the Suomi MPP satellite and the most updated emission factors from Andre 2019 to produce emissions for 46 species of gases and aerosols. The results are publicly available, and these are daily fire emissions for the whole globe at a resolution of around 500 meters, which is ideal for high-resolution model simulations. Here we decided to use the VIRS active fire product based on the I-band of the instrument because it has a higher resolution when compared against MODIS, and therefore is able to detect smaller fires. Some studies have compared the fire additive power from both MODIS and beers, and they have found that they are very comparable. Another advantage of beers is that it offers observations with no data gaps over the tropics. This figure summarizes our results. It shows the average annual carbon emissions in grams per square meter per year. You can notice that Africa is the region that is responsible for most of the carbon emissions from biomass burning, followed by the Amazon forest and the Southeast Asia. Fires in the tropic regions have a very well-defined annual cycle, reaching their peaks during their respective dry seasons. But at higher latitudes, such as in Canada and Siberia, there is higher interannual variability, possibly because these regions have also more variable interannual climate variations. Here you see an example of daily emissions from VFA for 2017. The purple colors represent low emissions, while the yellow colors represent high emissions. Sometimes large yellow circles appear and they represent very large fire events. Our inventory will be publicly available in a website that we are preparing. Before, I mentioned that fires from the other inventories could be misplaced in fine resolution model grids, and here's an example of this. This shows a time series for early August 2019 of a large fire that occurred in Washington state. This is how QFED maps this fire in its 10-kilometer resolution. However, if we map this fire into a 2.5-kilometer grid, this is how it looks like. You can see that the fire appears at 4 or 5 different fires because the model tries to find the closest grid box for each QFED geolocation. Now this is how VFA in its 500-meter resolution represents the same fire. You can notice much more detail in the variability and progression of the fire in a day-to-day transition. And when we map this into the model grid, this is the result. The advantages are evident. This is especially important when simulating fires in complex topography, because if you have a fire misplaced, then the smoke can be subject to different local circulation patterns and plume development. We compared our VFA emissions to the other 4 widely used inventories I mentioned before. These figures show the average annual emissions in teragrams per year of selected species that are shown in each column. So here we have GFED in black, fin version 1.5 in brown, fin version 2.4 in orange, QFED in blue, GFAS in green, and VFA in red. Each row represents different regions of the world that you can locate in the map. The first row of plots show the global average carbon emissions, and you can see that VFA is very much like the other inventories. This is true for most of the regions with very slight variations by species. However, we make use of the emission factors for boreal forests introduced recently by Andre 2019, and the regions of Siberia and Boreal America are the ones with the major differences among the inventories. So is a region that has large uncertainties because these emission factors are relatively new. So probably there is still some uncertainties for this biome. But just to remember, all the inventories are estimations and no observations are provided in this figure. After developing this emission inventory, we needed to test it to see how well it performs. So we conducted model simulations using WRF-Chem for 2 regions. One is Southern Africa during September 2016 to make use of the Oracle's campaign data, and 2 in North America during the summer 2019 to make use of the FireXAQ field experiment that was carried out there. The maps show the domains used for these simulations, and they show the total carbon emitted during this period. In the bottom, you can see a time series showing the total emissions of carbon per day of VFA and how it compares against the other 4 major inventories from before. These are our model results. The figure shows a comparison between MODIS MAYAC AOD versus our simulation that we named WRF VFA, and we also include CAMS reanalysis and MERA2 reanalysis for reference. In the top, we show the average AOD from each dataset during September 2016. And in the bottom left, there is a map showing the number of observations available that were weighted in this average. Then we show the biases from our model and reanalysis with respect to MODIS MAYAC. You can see that WRF VFA is able to reproduce the shape of the bloom in the locations shown in MODIS MAYAC, but there are possible overestimation in AOD in the region of Angola, which can go up to 0.1. The reanalysis, which include the data simulation of AOD, also reproduced the smoke plume but with different biases. We note that Dwarf Bife may be overestimating the AODs in the southern part of the continent, but this seems to be due to the different aerosol models used in the Modis-Mayak AOD algorithm. To prove this point, we also used AODs from Aeronet stations across this region. Here we present the data as time series for September 2016, where the black dots represent the AOD from Aeronet. The red line and red dots are the data from our model simulation, and also we included the AOD from Modis Mayak shown as blue crosses. Here you can see that the stations in the south, such as Windport and Bonanza, the model performs quite well with correlations above 0.86 and low biases, while it seems that Modis Maya greatly underestimates the AOD in these two locations, probably due to their regional aerosol model they used to derive AOD. The model also has good results in the stations that are closer to the fire emission source, such as Monguin in Zambia and Lubango in Angola, this later one with biases of around 0.09. The scatter plot shows how the model overall performs when compared against all the stations with data available during September 2016, showing that the overall AOD biases are around 0.03. When we compare against the airborne data from oracles, we also see some biases, but in general, the fittings and correlations are above 0.75 in the primarily emitted species such as carbon monoxide, black carbon, and organic carbon, which are shown in the top. The secondary species such as ozone, ammonium, and sulfate show higher biases and lower correlations, but this depends more in the model itself and its parameterizations rather than in VFAIT. However, we acknowledge that this is more difficult to prove. It is important to note that most of these flights were conducted at altitudes between 4 and 8 kilometers, where the model has thick layers and can also introduce errors when extracting the data at such altitudes. We also made a comparison against LiDAR data from the ER2 plane that was deployed during Oracle's 2016. Here in the left, there is an example of the smoke profile that is seen by the instrument and its uncertainty from the flight conducted on 12 September 2016. And in the right are the model results. We think that these are great improvements on simulating the smoke plume over the South Atlantic Ocean because the model is capable of reproducing the thickness and position and details of the smoke plume. As I said before, we also conducted a second simulation over North America, and we evaluated it similarly. Here you can see a similar comparison as before, covering the time frame between July 22nd and August 11, 2019. The emissions seem to be working well, but here it's more difficult to evaluate biomass burning alone because we have a lot of anthropogenic emissions, biogenic emissions that also play an important role. So isolating the case for biomass burning alone is more complex. Similarly, we compared against Aeronet stations, and here are the results. The overall AOD correlations are at 0.73 and slightly underestimating it by 0.01. We notice that the stations located over complex topography are the ones with higher biases, possibly because of model parameterizations are not capable or optimized for these regions. Now let's move to part 3, smoke dynamics and more precisely the plume rise process. Before starting, I want to give a little background on meteorology. Here you see a city and maybe you can notice the pollution and the clear sky. And then there is a very clear distinction between them given by the boundary layer height. Above this layer, you have the free troposphere. That is where all the largest gas circulation patterns is characterized by strong winds. The importance of this is that when pollutants stay in the boundary layer close to the surface, their effects are local. But when they reach the free troposphere, they can be transported up to thousands of kilometers away from its source. For example, volcanic eruptions or the fires that I showed at the beginning of this presentation injected material in the free troposphere or even the stratosphere that then transported all the smoke miles away. The processes that are involved in the development of a smoke plume are shown in this figure. The heat of the fire creates a strong positive buoyancy that transports the smoke upwards. But the smoke is also subject to the environment. For example, you have eddies and the edges of the plume that entrain colder air into the plume and other properties that can accelerate or suppress its development. Also, when the fires reach the boundary layer height, the smoke tends to show stratification. But if it's a fire large enough, then it will go to the free troposphere, where it can find moisture that could reaccelerate its development. It's in these cases when the smoke can have a long range transport and sometimes create a pyrocumulonimbus cloud. So, how high the smoke reaches in the atmosphere? As I said, it depends on the energy of the fire and the meteorological conditions. Unstable weather will enhance the convective energy of the plume and will make it reach higher altitudes, while very stable conditions will suppress it. We include this in models by using a model called plume rise. Plume rise was developed using lookup tables to calculate the injection heights, taking the atmospheric conditions from the host model. So it does know when the conditions are propitious for enhancing or suppressing the plume altitude. This first version of plume rise uses the data obtained from a field experiment conducted in South America. And the good thing of plume rise is that now models do not release the emissions at the surface layer, but can distribute it vertically as well. Plume rise provides the injection height at the altitude that the plume is estimated to have a vertical velocity lower than 1 meter per second, like you see in this example. The injection height will be between 5 and 6 kilometers. But is plume rise important? Well, this depends on your application. Let's consider two model grid columns, one with plume rise and another without it. Let's say that this is the boundary layer height and there are some fires in this grid box. Without plume rise, the emissions are released in the first layer of the model, and then the smoke is mixed within the boundary layer due to its turbulence. But when we use plume rise, we can provide a specific injection height and allow the plume to reach the higher levels to be transported far away. And this scheme represents how the model is embedded. Plume rise is embedded into each grid box of a host model that can be an atmospheric three-dimensional model, because then plume rise uses the atmospheric conditions given by the host model to calculate the injection height. This is an example of a model simulation for a fire that compares the impact of plume rise showing carbon monoxide and ppb. The panel in the left uses plume rise, while the panel in the right doesn't. The plots at the top are vertical cross-sections that go up to 10 kilometers altitude. The bottom plots show how the smoke is visible at 500 millibar level. You can notice that when we don't use plume rise, the smoke does not reach the high levels nor the free troposphere, and we tend to overpollute the surface. In contrast, when we use plume rise, the smoke reaches the free troposphere and then is transported far away by high wind speeds. This is another example that shows the benefit of using plume rise. The figures in the top show CO concentrations at 500 millibars level of the two cases, without and with plume rise. In the bottom, there is observations from the air sensors at the same level. It is evident that the use of plume rise creates a more realistic result than when we don't. However, we have conducted simulations with and without plume rise for Southern Africa, and we find that the plume rise may be overestimating the injection heights of these plumes, as you can see in the cross sections in the bottom. The reason for this is that fires in Africa tend to be small, with low energy, so they do not inject very high. In addition, the boundary layer height in this region is very deep during their fire season, reaching up to 5 kilometers in some areas, which may indicate that using plume rise in Southern Africa is just not necessary. Recently, plume rise have been developed to use the individual fire signals, such as fire relative power from satellites, to estimate the injection height. This is the same measure that we use to produce the fire emissions in VFA and replaces the lookup table that the previous version used. This new version of plume rise is currently being used in NOAA's hard smoke forecast. However, preliminary results indicate that plume rise may not be injecting high enough in the case of large fire events. Because of this, we are exploring new improvements related to the lateral entrainment that the plume can suffer during its development. Currently in plume rise, the entrainment is treated very simply, but we are investigating new formulations that are capable of accounting different factors. Under this perspective, a better entrainment scheme could account for the thermodynamic equilibrium that could reduce the buoyancy of the plume, and also account for the water vapor intrusion that, by releasing latent heat, could reaccelerate the plume rise. If results are good, this could mean that fires could be more accurately represented in models, especially large fire events that have impacts on climate, and also contributing to having more accurate weather and climate predictions of smoke and its interactions with the Earth system. Here you can see a short summary of my talk. I presented a brand new emission inventory based on the VIR's active fire product. And the main advantages of this new inventory is its very high resolution, that is around 500 meters, and that offers emissions for 46 species of aerosols and gases. I showed that at least for Southern Africa and North America, the emissions seem to be good, but we need further evaluation in other regions of the world. I also discussed the vertical distribution of smoke in models that is done by plume rise. Plume rise now uses the fire relative power to estimate the heat flux of the smoke plume, but it still underestimates the injection height of large fire events. To address this, we are improving the entrainment scheme within plume rise to include a thermodynamical approach. With this, I would like to thank you for your attention, and I will be happy to take any questions.